All right, today we're going to look at the intermediate value theorem, and it's a fairly obvious theorem, and we're going to illustrate it just with a graph of a particular function, and then we'll give the actual theorem itself. So here's the graph of a function. Notice this function is continuous on the interval from 0 to 3. It's continuous from the right at x equals 0 as we're approaching that point, which appears to be what, 0 comma 2, and then continuous from the left or from below at x equals 3. And on this interval then from x equals 0 to x equals 3, we can say the function is continuous, no holes, gaps, jumps, or other discontinuities. And all this theorem says is that if I have essentially what it says, if I have a function like this, so f of 0 is equal to 2, and f of 3 is equal to what? A little bit more than, right at a half, I guess. Let's just draw that in so we can sort of see where that value lies. Right, so down here. So what this theorem says that, let's say it's about a half, right? That's about 1/2. So on the interval from 0 to 3, f of 0 is 2, assuming this is the graph of the function f. F of 0 is 2, and f of 3 is 1/2. So if this is a continuous function, between these outputs, between 2 and a half, okay, so anywhere in between this, for any real number, and here I'm drawing a dashed line at about what looks like at about a y value of y equal 1.5, right? For any value though between 1/2 and 2, I can draw that horizontal line, let's say at 1.5 as I've drawn here. We will intersect the graph of the function at least once. We will intersect the graph at least once. And that should make sense. Essentially, think about it. If I take any function that's continuous, such that f of 0 is 2 and f of 3 is 1/2, if I try and draw the graph to basically connect this point to this point, making it continuous, I have to draw it without ever raising the pen or pencil off the paper. So eventually I'm going to have to cross this dashed line. And the minute I cross that dashed line, then we have some value of x in the interval from 0 to 3 where the output is equal to, in this case, 1.5. And so the intermediate value theorem says that there isn't, for any intermediate value, any value between your outputs at your endpoint, so to speak, there must be at least some input on that interval that will give you that corresponding output. So there's at least one value on the interval from 0 to 3 where f of one value x on the interval from 0 to 3 where f of x is equal to 1.5. And so that's the idea of the intermediate value theorem. Of course, it only works if the function is continuous. If it's not continuous, I can kind of have a hole up here and I can jump down, have a jump discontinuity where it's not continuous, and then I can continue on to this point and never touch that dashed line. Okay, or something like a vertical asymptote, right? I can go up to infinity here, go down to minus infinity here, and never cross that line. But if the function is continuous on the closed interval from a to b, so in this case I was looking at a being 0 and b being 3, then for every value capital M, and for my value, the capital M was here, this was about 1.5, between f of a and f of b, right? So here was f of a, f of 0 was 2, f of b, f of 3 is 0.5. So between 0.5 and 2, for any value, any horizontal line I draw is going to hit the graph at least once. So there exists at least one value c in the interval from a to b such that f of c is equal to m. And there could be more than one. I mean, I could have the function come down, sort of like a sine or cosine function, up and down a few times, and then get to that point. So it could be more than one, but there's at least one. And so intermediate value theorem is an existence theorem. So one thing we can do is if we have a function and we want to know what our well, this says solutions. Really, this should be, let's show that this function has at least one root, is what I meant to say here. We'll get to solutions in a sense. Show that this function has at least one root, or 0, on the interval from 0 to 2. And so, what we're saying then, is there a value of x that makes this function equal to 0? Okay, so it's a root, or sometimes we call it a 0 of the function. And notice if I plug in 0 into the function, what do I get? 0 to the 4th is 0. Sine of 0 is 0. 0 minus 0 minus 10 is negative 10. F of 2 is going to be 2 to the 4th minus sine of 2 minus 10. Now 2 to the 4th is 16. Sine of 2, I don't know exactly what it is. I can use the calculator. But it is going to be clearly less than 1, right? Because the sign is always between -1 and 1. So the biggest this can be is 1. So this 16, let's say it's close to 1. 16 minus 1 minus 10 is 16 minus 11. This value could be 5. Do my subtraction. I'm not too good with that, huh? 16 minus 11 is 5. Right? It could be 5. Or it could be more, because sine of 2 could be less than 1. Let's just go ahead and figure out what that is. I've actually entered that function in the calculator. And so I'll go to the table. We'll just reiterate that we did before. When we plugged in 0, we got negative 10. And when we plug in 2, I said 5, maybe a little bit more, and I do indeed get a little bit more than 5, so it's 5.09 about. But the point is, right, we were saying show that this has a root or 0. Show that there's a value of x that makes the function 0 on this interval. Right? Well, notice at the endpoint 0 it's negative, right? It's less than 0. And at the endpoint 2 it's positive, it's greater than 0. That means there has, in between negative 10 and 5.09, we are going to have a value of x, right, such that the functional value output is between these two numbers, right? So that's true for any number between negative 10 and 5.09. And 0 is indeed in between these two numbers, right? 0 is in between these two numbers. So there's that. So by the intermediate value theorem, there is we'll call it C, in the interval from 0 to 2, such that, and I did the open interval because clearly I know it's not equal to 0 at 0 or at 2, right? Such that A is equal to 0. F of C is equal to 0. And so we know there's at least one root, right? At least one root. Okay. Now, of course, we have technology, and we sort of maybe take for granted that, and we just say, well, why do we even need this theorem? I can just graph it down here. Here's the graph of that function f of x. And we can clearly see, right, at f of 0 it was negative 10. At f of 2 it was about 5.09. And we can clearly see here, right here, is the 0 or the root of the function. Approximately 1.5, between 1.5 and 2, about 1.8 maybe, or something, right? So we can certainly do that. But keep in mind that numerically now estimating that 0, we're going to look at a routine for that, but this indeed allows us to see the existence of at least one 0 on that interval and gives us an idea of where to look. We might not even know how to open up the viewing window to see where the 0 is, right? But we can know for certain that there's at least one root on the interval from 0 to 2 for this function with the intermediate value theorem. Let's look at this. How can we estimate that root a little bit better? first of all, if a function is continuous on the closed interval from a to b, and f of a and f of b are non-zero and have opposite signs, then f has a 0 on that interval. And that's basically what we showed, right? We just showed for f of 0 was equal to negative 10, right? It was negative. F of 2 is positive, and so since we have alternating signs, we know there's some point where the output has to be 0, right? It's, if we were looking at the graph, we would have two endpoints whose values, one was positive, one negative. That means that we would be 0 at least once. Okay. Now, question is though, how do we find it? And one answer is the so-called bisection method. And I'm just going to illustrate this method to you, because what I want to do is go back to the original function. We've already shown that it has a 0, a root on this interval. Let's find an interval of length 1/8, or about 0.125, that contains the 0 of this function. We'll stop there, and then I'll kind of explain where this could lead to. So we already know from the previous analysis that f of 0 was negative 10, and that f of 2 was about positive 5.09. Sorry about that. 5.09. Okay, and so certainly the interval from 0 to 2 contains at least 1 0, right? Okay, but the length of that interval is what? From 0 to 2, the length is 2. The length is 2. Okay, so how can we proceed? How can we sort of narrow down in on things? It's called the bisection method because what we do now is we bisect the interval from 0 to 2. In other words, we just take the average of 0 and 2. What's halfway between 0 and 2? 1, right? 0 plus 2 divided by 2 gives me 1. And so what I'm interested in now, what is f of 1? So now I'm going to plug 1 into this same function. I'm going to use the calculator, which I already have entered in that function in there. If I plug in 1, I get negative 9.84 about. Okay. And so remember, when we plugged in 0, we got a negative 10. I'm going to put a little negative sign over this. And when we plugged in 2, we got positive 5.09. Well, now, in between at 1, we're negative. So this tells me that I can shrink the interval down. Instead of going from 0 to 2, I can now go from 1 to 2, right? Knowing that 1, again, we are negative. At 2, we're still positive. So since there's a change in sign for the outputs at 1 and 2, I know in between 1 and 2, there's at least one value where the output of the function is equal to 0. And the length we've cut in half is now 1, right? Bisected. So each time I do this step, I'm going to cut it in half. Now I'm going to take halfway between 1 and 2, right? So if I take 1 plus 2 and divide it by 2, I get 3/2 or 1 1/2. So now I'm going to look at what is f of 1 1/2 about. Negative 5.9. And now since it's negative, what's going to happen? I'm going to replace, instead of starting at 1 where it's negative, I can now start at what? 1 1/2. I know f of 1 1/2 is a negative number. F of 2 we still know is positive. And so our interval is now a half. All right. Continue. What's halfway between 1 1/2 and 2? Answer. Equals 1.75. Right? And so f of 1.75 is about what? Negative 1.6 again. Or negative again, I should say. Right? So again, I can shrink this down now from 1.75, where it's negative, to 2, where it's positive. Now our length is 0.25. Okay, and I'm going to do it one more time. So halfway between 1.75 and 2, we get 1.875. And 1.875 is about 1.4. Now notice this is positive, so what I'm going to do now is replace the positive 2 where the output was positive. I'm going to go from 1.75 to 1.875. So we know the output was negative at 1.75, and at 1.875 the output is positive now. And notice this length is 0.125 or 1/8. Right? So our answer is an interval of length 1/8 or 0.125 that contains our solution is this one. I know it's not the endpoints, right, because neither one was equal to 0, but somewhere in between here there is a value of x that will make the function equal to 0. Okay, we're going to stop there, but do you get the flow of things? Each time I do a step in this process, I cut the interval in half. Right? And so I'm shrinking it down. So the next one would be to take the average of these two numbers, the midpoint of this interval, check the functional value, and then we will be able to cut it in half again. It will be 1/16, right? From 1/8 to 1/16, and so on. And how accurate do you want to be? Well, you can continue that process as long as you want until you're within 1 divided by 2 to the 10th power, which is about 1 in 1,000. And so you can see how we can estimate the solutions to equations with this so-called bisection method, or trying to find the zero of this function, which is not easy to do, right? This is, when we just gave you this function, what are the zeros? We wouldn't know how to proceed really because of the fact there's a algebraic term and a trigonometric term combined together. Okay, now obviously manually doing this process, we don't want to, if we were trying to use this method, that can be a little tedious. But if you're a computer science person, you could easily program this routine. It's not hard, right, to have it check the values, compare, and then compute this midpoint, compute that value, compare the values, and then readjust, and so on. And you can have that loop through really quickly and get real accurate interval where your solution lies. You can be within accurate to the 3rd or 4th or 5th decimal place. Okay. So this might give you some idea about how you could write an equation solver. For instance, a lot of the TI calculators have an equation solver. How do they solve equations? Well, it's actually not this method that they use, but this is a method that can be done. Let's do this method and talk about solving an equation. How can I solve an equation? If I have an equation, how can I solve it? Let's first of all, how do I show that this equation has a solution on the interval from 0 to 1? Is this different from what we were looking at in finding the root of a function? Well, we're going to make it the same, and what I'm going to do is in this equation here, I'm going to set it equal to 0 by simply subtracting 1 from both sides. So the minute I do that, so any equation you have, bring everything over to one side, set it equal to 0, and now this side over here we're going to call the function f of x, and now we're right back to the same problem that we were just looking at, which was find a 0 or root of this function. So in my previous example I had something about finding a solution. Originally I think I was thinking about an equation, and so it's really one and the same thing. So when we're trying to find the root to f of x equals 0, it's going to be the same as the solution to this equation. The solution to this equation is the root roots or zeros of this function. Okay, let's first of all show that it has a solution on this interval. So f of 0 is going to be the natural log of 5 minus 1, and f of 1 is going to be the natural log of 6 minus 2 minus 1. Okay. Well, we'll use our calculator again to help us out with this. I'm going to enter in that as my new function. So I've got the natural log, let's clear that out, natural log of x plus 5 minus 2x minus 1. Go to the table. I've got 0 and I've got 1. Delete these other values. So at 0 it's 0.609, which is greater than 0. At 1 it is negative 1.2, which is less than 0. So that tells us there is a solution in this interval. The interval from 0 to 1. The length of that interval, of course, is 1 unit long, right? 1 minus 0 is 1. So we'll continue with the bisection method, right? I'll look at halfway between 0 and 1. It's 0, that's 0.5. I'll plug in 0.5. I get what? Negative 0.2953, which is about, we just rounded off to negative 0.3, but it's less than 0, right? And again, the 0, we were what? Positive, and at the 1 value, negative 1.2 is the output, we're negative. So now our interval is going to be what? From 0 to 0.5. Again, output at 0 is positive, output at a half was negative. The length is now a half. Halfway between 0 and a half is 0.25. See what we get when we plug in 0.25. Positive 0.16 about. Positive though, so what's our new interval going to be now? We're going to replace the positive value that was at 0 with 0.25. We're going to squeeze in a little bit. Now cut that interval in half. Here's where the output is positive. Here's where it's negative. Our length is 0.25. And we're going to do one more. What's halfway between 0.25 and 0.5? That's 0.375, right? So again, that's halfway between, or the average of 0.25 and 0.5. Okay, what is the output when we plug in 0.375? It's negative, just barely negative, 0.06. And therefore, what am I going to replace? This negative 0.5, it was negative, now we can replace that with 0.375. And that length is 0.125. And so here is my desired interval in this problem, and we've asked to stop there. But again, the process can continue and you can get as accurate as you want to. Okay. Of course, in the process, it could be that you plug in a value and in one of these steps and you get exactly 0. Well, if you get exactly 0, you found the actual solutions, right? So you could be done. You can terminate the process at that point. But typically, it's, you know, you get closer and closer, zooming in on the value. So this is the bisection method, and of course the intermediate value theorem before that. Nice little idea about how we can think about what we call numerically estimating solutions to equations, like this example illustrates. And at the end of the course, we're going to look at another method that's probably more along the lines of what your calculator or some other algebraic software might use to find solutions to equations, something called Newton's method, but we'll look at that at the end of the course.